Okay, so now here we are in chapter 13 and just one more chapter to go. And now this chapter is about analysis of variance. We will talk about that. In fact, the abbreviation for analysis of variance is ANOVA. We will talk more about this as we go along. Now, actually, what is the purpose of this chapter? It is to compare several means. Remember in chapter 12, we did hypothesis testing and also we came up with a confidence interval formula to make inferences about difference between two means. Okay, so in other words, you are comparing two different means. It is kind of like birth weights of male babies. The birth weight differences between male babies and female babies. But of course, you have lots of situations where you will have not necessarily two groups that you need to compare. You can have several, and you can think of lots of situations, right? Lot of situations. Now, just it's a very simple example here. What if you want to see the differences in the effect of exercise, diet, and meditation on blood sugar? Okay, like some people say exercise really helps in the blood sugar reduction, and then diet also, of course. You need to reduce your sugar consumption, right? And then also, some people believe, and it may be even proven, that blood sugar goes up due to stress. So even meditation could help. So now if you want to see whether the mean differences between the blood sugar levels based on these three different therapies, you need to sort of, you are in a situation where you have three groups and you need to compare. Okay. Um, okay, so let's see how we can, extend this idea that we had in chapter 12 in comparing two different means into like more than two means, several of them, three or four or more. Okay, all right. So let's go to the next slide. In the next slide, here it's giving the review of the chapter. So typically when you do any experiment and then when you have some data analysis, you like to get a preliminary overview of the whole thing. Now, descriptive statistics that we learned earlier will help us, like stem plots, box plots, the summary statistics like mean, standard deviation and stuff. So that would help us to sort of get an idea. Okay, is there really like a difference in means, among these groups and so forth. Okay, then we will talk about an issue that arises because you have several means. Now, if you have just two different means, you have only one comparison to make. If you have more than two means, you will have several pairs of means, right? See, when you compare, you always have a pair. If you have more than two, there will be, there will be more than one pair comparison that you have to make. So in other words, you will have multiple comparisons. So when you have multiple comparisons, there is a problem, okay? So which we will talk about, so that that will motivate us to sort of slightly change the procedure, and then that would, how we can change is by using this technique called analysis of variance. So we will learn about that, and then after we do analysis of variance, that will really have a test of hypothesis based on the results there, depending on whether we reject or accept the null hypothesis, which means that, okay, we will either decide based on this analysis of variance data analysis, we will decide there are no differences or there is at least one difference. So if there is at least one difference, we need to know where exactly they are, what exactly, which of the pairs are exactly different from each other. Okay, and then you need to do comparisons pairwise. Okay, and it's a post hoc, that means after the effect kind of, and then you will do pairwise comparisons. And then, of course, in order to do this stuff, there are certain assumptions, specifically equal variance assumption. That means, you have to assume that variances within each group is the same. Now, we are not going to worry too much about that, but I just want to include the slides. So 13.5, you don't have to be, I'm not holding you responsible for 13.5. And then 13.6 is an introduction to non-parametric tests. Again, now this is just an introduction. Even this section, you don't have to worry about as far as the tests go, because this is a basic stat class. We don't have to go into depth to this. In fact, non-parametric statistics by itself is a course or maybe several courses. But the idea here in including this is to expose you to several different techniques, and if you're further interested, you can take more courses. Okay, so as far as the course goes, or the grading or assessment goes, you need to be concerned about 13.1 to 13.4. So I will just write it in here. Course grading or course assessment, I'll say assessment is based on 13.1 to 13.4 only. Okay, all right then. So let's go to the next one. Okay, in fact, this is an example, which illustrates the idea here. Now, see, here you have the response to be the heart rate, okay, of people. And then now this is sort of like a study in psychology. Okay, so how is the heart rate affected, or how is the heart rate influenced by different things, like by having a pet dog as a companion, or by having a human friend, or just staying alone. Okay, so these are the 3 different group characteristics. So based on these 3 different characteristics, we need to see whether the heart rates differ significantly from each other. Okay, what is better, or are 2 of these equally the same? Okay, things like that. All right. Okay, so this is the idea of a comparison of several means. So there will be actually, in this example, 3 different mean heart rates, right? Mean heart rate from group 1, that means those who have been in the companionship of a dog or pet dog. And then group 2, if you have a friend. Group 3 is if you are just by yourself. Okay, all right then. So let's go to the next one. So now typically data would be like this. So group 1, group 2, group 3 data will be in here. And if you count, you will see that there are 15 individuals on each. So these are the heart rates. Now, lots of times in software, software do not like to have the data like this, because what if you have 10 groups? Then there will be like 10 columns of data. Typically, what you want to do is you want to make it, you want to sort of change the structure of this and then have all this information only into 2 columns. In other words, you will put all these 45 heart rates, which is 15 times 3, into 1 column, which we can call to be heart rate. Okay, and then that is like your Y, because these are the responses, and in biostatistics terms, these are the outcomes. So you will have 45 outcomes depending on the exposure. So there are 3 different exposure levels. So now the one column will have the outcome and the other column will have the exposure. And how will you distinguish between the 3 different groups? You can code them 1, 2, 3. Okay, so typically that's how you prepare the data to do any data analysis. So let's see, that's what this slide is telling. And especially, in fact, they're talking about SPSS, which which I talked about earlier. SPSS is a software that is very widely used in public health. And then, so here's the screen for SPSS. So you will have to enter the data like this. So you have 3 groups. So from each group, you will have heart rates, and then there will be like this. 2 columns with 45 rows. Okay, all right. So that's just to let you know that it's just a matter of preparing the data for software. Okay, and then let's go in here. So now we'll begin descriptive statistics. First of all, see, just to get an idea, is there really a big deal about these two different characteristics? So you can kind of find the sample mean for each group. So now you have the heart rate, for mean heart rate, actually, see x bar I. Now look, I is a dummy variable and I varies from 1 to 3, right? So then, so the sample mean in the group where pets were companions, you have 73. Then if you had a friend, it is 91. If neither, it's 82. This is pretty high. So it looks like as if with pets, it's much less, right? The heart rate is much less. With friends, it is really high. And then, this is like a little bit close to each other. But we can sort of get an idea, actually, especially if you compare these two, there seems to be a big difference, right? 73 to 91. So we sort of get a hunch that, okay, there is a, group effect, for this heart rate, right? But we need to statistically, prove that, or at least, confirm our claim. Okay, so how we do that is as follows. Okay, so now we saw with summary statistics. Now, in addition to summary statistics, we could get some visual aids. Now, that is called exploratory data analysis. In fact, the person who introduced this is John Tukey, who was a statistics professor at Princeton University. He came up with these ideas: stem plots, box plots. We have come across this before, right? And then also dot plots. And that those are really neat. Of course, this is pretty recent in a way. I mean, like in this, he came up with this in the 80s. But before that, statistics was mainly numbers. But with the computers and everything, and with these methods, we sort of get nice pictures, which tells us the story about data as well. Okay, so once you get the summary statistics, next thing could be to get some stem plots. Okay, so let's see how that looks. So in the next slide. Okay, so here are the stem plots. Like stem plots are the same as stem and leaf, remember? So you can kind of see now. Remember first of all that the data is increasing this way. So the pet companionship group have, if you remember, the heart rate data to be lower, and then this is with a friend, this is with neither. So you can sort of see that here it is sort of in this area, right? The mean is around this area, and then in here the mean is in this area, and then for the third group, mean would be in there. So you can sort of see that there is definitely a difference between these two, and these could be close to each other. We do not know. I mean, statistically, we have to confirm ourselves about this. Okay, but again, the stem plot also tells us the same story, that there should be differences, in the groups. Okay, that means these characteristics make a difference as far as the heart rate goes. Okay, stem plots. I like this. Look, in the stem plots, of course, here we in the stem plot, more than the mean. Actually, the mean is, we cannot make sense of the mean value using stem plots. If you remember, these horizontal lines are the median values, right? So stem plots go with medians. Now, even if you look at medians, see, from means using summary statistics, we knew that there would be a difference, and heart rate being the highest for the friend group, right? um, Even with the median, you can see certainly the same story. Okay, see, even if you compare medians. Okay, all right. So just trying to get a bigger picture with all these different tools that we have. Okay, all right. So then now formally let's think about how we put this into symbols, and then start doing some data analysis. Okay, so now if you are to sort of put this problem into notation and then develop hypothesis, if we are to go along with like what we did in chapter 12, where we had only two different means, we could set up our null hypothesis like this. Because we have three different groups, if you have three different groups, you will have like, you will have to compare first with the second, first with the third, and second with the third, right? Because if you have, you will have certain number of pairs. In fact, there is a formula that tells us how many pairs are there, if you have certain number of groups. Actually, we have done this before. Remember in the binomial that n choose r, that is a formula which will give us the number of pairs. So here, the number of groups is 3. So out of 3, how many pairs can you make? It is 3 choose 2. Okay. Just to let you know, how we can use what we have learned. So if you sort of figure out 3 choose 2 using that factorials and stuff, you will get 3 choose 2 equal to 3, and that is why you have 3 different null hypotheses. Okay. Now, of course, if you have 5 groups, you will have 5 choose 2. I think 5 choose 2 works out to be like 10, I think. So, you will have 10 hypotheses, 10 null hypotheses. I mean, that's going to be really messy. Okay. So this kind of pairwise comparisons and writing down null hypothesis like this is going to be really cumbersome, even in writing it down, especially if you have lots of groups. Okay. And actually, in addition to that messiness, there is another issue. Okay, so let's see what that is. Okay, so let me go to the next slide. Okay, so the next one is actually a little bit more serious. Now, remember, whenever we do a hypothesis test, we know that we never can make the correct decision. Like we are not 100% sure that we make the correct decision. And then in fact, we came up with that alpha, remember? Alpha, which is called the significance level. And that is actually probability of rejecting H null when it is true, which is a mistake, right? So we are taking like a alpha % chance in making this mistake. So what is this mistake? It is a false rejection of H null, right? Rejecting H null when it is true is a false rejection of H null. So probability, I need to put parentheses in here. Probability of a false rejection of H null, when we did in chapter 12 or even before, we will decide what kind of a risk are we taking. We will usually say alpha will be 0.05. If you are doing medical tests, maybe we will even go further down, 0.01 and so forth. Okay. So we set alpha equal to 0.05, say we set it. But even if you set it, because of these lots of different pairs and like multiple comparisons, we will not end up getting alpha to be 0.05. So let's see how that works. Let me sort of, walk you through this. Now, first of all, since we have several null hypotheses, we cannot just say probability of rejecting H null. There are several of them. So let's define the probability that at least one of them will be rejected falsely. Okay, so probability of at least one false rejection of H null, because there will be several of them, right? So then that is the definition of family-wise error rate, because there's like a family of null hypotheses. There are, if there are 5 pairs, there will be 5 null hypotheses, right? So then, now let's assume that all these hypotheses are true. Now we are setting our alpha, which is the type 1 error, right, which we call to be the significance level. We are setting it to be 0.05. We would like to have a 5% chance of making a mistake. And now the probability of retaining, now let's keep with this and then let's figure out how much this will work out to be. Okay, so this is where the probability working is. So let's first of all calculate probability of retaining all 3 null hypotheses. Okay, so that means now in the previous example there were 3 of them. So if all three were to be accepted, retain means accepted, the first one has to be accepted, second one has to be accepted, and the third one has to be accepted. So this event is an AND event, probability of A and B and C. Now, if you remember in probability, we said that if the events are independent, to get that AND probability, you can multiply them. So that is why I have multiplied the single event probabilities. So probability of retaining the first one times the second one times the third one. Now these all have the same probability. See, now probability of rejecting H null when it is true, remember we are doing this whole business assuming that they are true. Probability of rejecting, we have said, okay, is 0.05 for each one of them. So probability of retaining, it will be 1 minus, because either you will reject or retain H null. So if you are not rejecting, you will retain it, so that will be 1 minus. So this probability will be the same for each one of these events. So you have to multiply it, multiply it 3 times, which is like cubing it, and then you will get the answer to be 0.857, right? So now, so this is just one thing that we found to find this. See, that is what we need, right? Probability of rejecting at least one is the same as probability of rejecting at least one is the complement of keeping all three, right? So which means this probability will be 1 minus this probability. Now this probability is 0.857. So you will have 1 minus 0.8, oops, this is 857. Okay, I think, did I make a mistake? So then, so yes, 1 minus 0.857. Oops. That should come to 0.143, right? So now look, this is the probability of at least one false rejection of H null, which is the family-wise error rate. Even though we would ideally like to take only a 5% chance, if you do a multiple comparison with 3 groups, you will get the error rate to be 0.143, which is pretty high. That means there is a chance of rejecting at least one H null falsely with 14.3% chance. That's pretty high. Okay, so even if you start with or even if you like to have the small probability of making the mistake, you will end up with the probability of making the error to be much higher. Okay, so that is the problem with multiple comparisons. And then, accuracy is so important. You need to give reliable results. So when you have the error to be this high, your data analysis is not going to be worthwhile at all. So that is one big problem with multiple comparisons. So we have to remedy this, and that is what this topic of analysis of variance is about. Okay, so let's go to the next slide. Okay, so that's so just to continue with talking about it. In fact, you can see that in fact, if you have the number of groups to be increasing, you can in fact, using that formula I told you, k choose 2 will give you the number of pairs. So, and you can work it out. Remember I told that if you have 5 groups, there will be 10 pairs. That is like 5 choose 2 will work out to be 10 using that formula, remember, which we did in binomial. I don't expect you to know this, but just in case you are curious, how we apply what we have learned. This is a good situation. Okay, so how you get these numbers is using that formula: 5 choose 2, 6 choose 2, 7 choose 2, and so forth. Now, what is important for this lesson is just look how many pairs. Here it's 45, and if you are to write H naughts or H nulls for all these, there will be 45 H nulls with 10 groups. With 8 groups, it will be 28. Even that's bad enough. And then the probability of making that family-wise error is really, really high. Look, it's really going higher and high. Okay, these are not acceptable at all. So we have to think of something else. Okay. Okay, so here's the way that the statisticians have remedied it. Okay, that multiple comparison error rate problem. So it is like a two-step approach. First, you do a overall significance. That means you are looking to say, okay, is there at least, or could it be that all groups are the same? That is like your null hypothesis. Your null hypothesis is going to be all group means are the same. And your alternative will be at least one of them will differ. So to do that test of hypothesis, we will use this technique called analysis of variance. And then the abbreviation is ANOVA, A-N-O-V-A. It's very easy to say that way, ANOVA. And then, once we do this procedure, it is a hypothesis testing procedure. And then if you accept HA, that means there is at least one pair of means, which is significantly different from 0. That means that pair, in that pair, the two means are different from each other. Then you will do individual pairwise comparisons. Okay, so that these are the two different steps involved. So we first do an overall test of hypothesis. Okay, and that is using analysis of variance. So in this slide, we are sort of talking about what analysis of variance is. First of all, just to give you some description of analysis of variance. Now here we are talking about one way. Now one way means, we have only one x. One way means one x. In our example, it was like with the group, right? Now you could have the group and the age of the person to be, of course, age affects heart rate also. You can have age categories. Then it will be not one way, it will be two ways, because there will be two different types of x's. But here we are working with only one way, so that one x, so that is why it's called one way analysis of variance. Now, typically for a one way ANOVA, you will have the exposure. Remember, exposure is the x, right? That's why I use the letter x, because we are sort of familiar with y and x, right? Even from math, y always depends on x. And remember, in biostatistics, the term used is exposure. Now, when you do ANOVA, when exposure is categorical and y is quantitative, okay, most times it will be like continuous, okay, and then the purpose is to test if group means are different statistically, okay. All right, then how we set it up? Statistically, use always whenever you have to do a test of hypothesis, we have to come up with the H null and the HA. So H null says there are no mean differences, all group means are the same. HA says the opposite of this, at least one pair of the mu's will differ, okay. And then you use the method. Now here we are, of course, we are getting to know a new statistic called F statistic. Now F statistic is a ratio of variability, okay. Typically, like even if you, this is just the first time that we are learning it here, but F statistic is a very common statistic. Later on, if you do more stat classes, you will come across this. Typically, just to let you know, it's a ratio of variability. I think I spelled it wrong. And then how is variability measured? It is measured in terms of sums of squares. See, these sums of squares, if you think carefully, is like standard, at least variance formula. See, remember you take x minus x bar, and then you square it, and then you sum it up, okay? So variability is measured in terms of sum of squares, and then the F statistic will be a ratio of two different types of variability, okay? Now, what are these two types for this ANOVA? You will compare the variability between groups. So if the group means are different, the sum of squares that is coming from that will be much higher. Okay, you will compare that to variability within groups. Variability within groups is like the typical, random noise. The difference that occurs because I am different from you. Okay, so it's like the person to person or item to item difference. Okay, so if the between group variability is very much higher than the random noise variability, you can so certainly deduce that the group means are different. At least one of them will be different, because we will reject H null and then we'll go with H8. Okay. Okay, so now what is variability between groups? Now, how we sort of quantify that is, you will take the sample mean for each group. Okay, sample mean for each group, and then you will take the difference between each one of them from the grand mean. Grand mean means you will take the sum, the mean of all the data. In that example, that will be the mean based on 45 observations. Okay, the group means will be, now for that particular example, each group mean will have 15 observations, right, coming from group 1, group 2, and group 3. So you will have three different means in that example. You will take the difference between each of these and the one whole big grand mean. Okay, and then if these are very different, even if you square it, that difference will remain the same, and then the variability will be really high, and that will signal a group difference. Okay, now that statistic is called the mean square between groups. So MSB, B stands for between. See, now we need to pay attention to this last letter. B means between. Then within will be having W in here. Okay, now so first of all, you will get the sum of squares between groups, very similar to standard deviation. And then there is something called degrees of freedom between groups. Okay, and then here we are sort of understanding the notation. K stands for number of groups, and then X bar is the grand mean, and X bar I would be the mean group of I. Okay, so just be familiar with this notation. And then here it says, okay, how to calculate it. So sum of squares between groups will be, so the group mean minus the grand mean, and we have to make some adjustments in case each group has different number of items or individuals. We need to make some adjustments, right? So you need to multiply by ni, and then further again to standardize the number of groups, because see, if you have this k being 10, this will really be high compared to k being 3. So you need to sort of standardize it with respect to the number of groups as well. So because of that, you will divide by k minus 1. Okay. Now this is the formula for MSB. Okay, MSB is going to be important. This will be the numerator of the F statistic we are going to work with. Okay. All right. So here's a picture. Now these little x bar 1, x bar 2, x bar 3 are the sample means for the three different groups. These are the heart rate means, sample means, and this is the grand mean. This is based on 45 observations, all 45 of them. Now these are the differences. So actually you will square each one of these, and then you will multiply by 15 in here, because N1 is 15, and then you will get the SSB. Okay, now look, the third group mean is so close to the grand mean. Now actually, if these also were very close to grand mean, that means all these three groups have the same mean heart rate. But the fact that these are much above and much below means that there's definitely a difference among the three groups as far as the heart rate goes. Okay, so visually we can sort of convince ourselves of that. Okay, so now let's go in here. So here this slide shows how to calculate by how you plug in the numbers. You can go over it yourself. This is like the x bar 1, that is the pet mean heart rate, right? This is like x bar 2, this is the friend mean heart rate. This is like the neither or nobody mean heart rate. And then 82.44 is the grand mean, that means based on all 45. Okay, now degrees of freedom for between is number of groups minus 1, which is 2. Okay, And then of course to get the MSB you need to divide this by this, and then you will get this. Okay. Alright, so we are just paving our way to doing the statistic. Okay, now to go into variability within groups. Now within groups means there is variability coming from, like as far as the heart rate, that example goes. Of course the heart rate varies even if you have 15 patients with the pet as the companion. There are differences within them. Okay, so now within groups is a reflection of that. Okay, and that is because of noise, because I am different from you. Okay, all right, now it's the same notation except that the subscript changes W, and then actually the variance here, the variance within, is actually standard deviation for each one of them. And then what you will do is, of course, you will sort of adjust it to take into account if there are group size differences. Okay, so it's the same idea. So let's see how that works. um, uh, so here, just to adjust, you of course, in here you will multiply by ni minus 1. Of course, not ni. In the first one it was ni, here it is ni minus 1. Now there are reasons for using minus 1. Of course, there are theoretically proven, statistically sound reasons which you can learn while later on if you do a higher level class. But here right now you have to believe me and the book. These adjustments are justified. Okay, and then the degrees of freedom will be big N minus K. Big N means the total number of observations, and then in that example it's 45. K would be the number of groups, which is 3. Okay, all right, so then actually yeah, so right here this is the picture of within group. See, now you have for each different group you will have a mean. This is like x bar 1, this is x bar 2, right? And then not every patient who had pet dog as a companion will have the heart rate to be the mean value. It will vary. So the difference between each single one of them minus and this sample mean will give you the mean square or the sum square within group. So there will be 3 such, and then you will adjust by multiplying by ni minus 1. Remember the previous slide, and then you will get the sum squares within. See, the subscript W stands for within. And so the same thing, you just plug in the numbers, and this shows how you get the answer for SSW. Again, MSW is dividing by the degrees of freedom. Always this is true. Mean square will be actually sum squares divided by the appropriate degrees of freedom. No matter which class you do, what method you use, to find the mean square, you need to get the sum square divided by the degrees of freedom. Okay, of course there are formulas for each one of these. Okay, so let's go to the next slide. Yeah, okay. Okay, so now in this slide, this is actually the most important as far as the ANOVA technique goes. You have this table. In fact, this is called the ANOVA table. Actually, what I did was, this came from the book. I just added this. This is like the general formula, okay? Always, of course, for a one way, there are 2 different sources between groups and within groups. Of course, for more complicated situations, the table gets more complicated. Now, typically, you will have the sum squares column, degrees of freedom, and the mean square. Now, if you look in here, how you get the mean square is dividing sum squares by the DF. Okay, I just put that. And then sum squares, we knew the formulas. We sort of went over that. Degrees of freedom, remember, we had the formulas. And then to get the mean sum squares, you divide this by this, you get that. You can in fact check this divided by this will give you this. This divided by this will give you this. Okay, and then another thing to note is that degrees of freedom, this plus this will add to this. And always, I mean, there is a formula of how to get the total. always remember this, ANOVA table, the degrees of freedom from each of these sources should add to the total degrees of freedom. Okay. All right then. So now, finally, this is what we need, right? F statistic. How do you get the F statistic? You need to divide the two different mean squares. Mean square between, mean square within. Now look, mean square between is so much higher than mean square within. What is this mean square between? What is it? It is the contribution of the differences between the groups, right? That means because the the heart rate due to different groups is varying so much, this became so much larger than the random noise. Random noise, which is actually the within group variability, which is a result of difference between one person to the other. Okay, so this, which is like random error, is so much less compared to the the difference that occurs because of the, the, the group characteristics. Okay, so this statistic is a reflection of the difference, and then you will calculate that. Now, so F statistic, in fact, is actually this. This says, it is like the signal to noise ratio. Signal is what we are after. Does it signal that there is a group difference? How we do that is even like observations have a little noise. Is the signal much more significantly different from the little noise that we have? Okay, so if it is different, this F will be very high. Okay, so that's the idea. Okay, of course, mathematically these are really sound. All these results are proven mathematically. Okay, so you can certainly go along with this with no hesitation. Okay, and then now if statistic again is a mm, mm, has a distribution. Okay, so should I written it in here? Let's see. F distribution um, distribution is based on two types of degrees of freedom. Okay, I still haven't shown you in the slide, but you will see it. So numerator df and denominator df. Okay, now this is true always. No matter when you use the F statistic, it will be a ratio between two variances or two variabilities, and then coupled with that you will have two different types of degrees of freedom. The numerator degrees of freedom, see, let me put that in here, and the denominator degrees of freedom. Actually, the numerator degrees of freedom will be the degrees of freedom which is coming from the numerator, so it will be 2. Denominator degrees of freedom here will be 42. Okay, so you need these to refer to the tables. Okay, so now we did a test of hypothesis. Always with the test of hypothesis, you have a p-value that we need to think about, right? So to get the p-value, you can refer to the tables or you can use a computer program. Okay, now again, as we said, there is this numerator degrees of freedom. Now the book uses df1 and df2, and then actually they are, the df1 in here is the between degrees of freedom, df2 is the within degrees of freedom. Okay, so let's see how that works. You will have the F statistic table, table D in your book, or you can even use software. So so the critical values, remember, it is like the boundary of the rejection region, right? Now, so the numerator degrees of freedom is on top, and then on the left column you will have the denominator degrees of freedom, so this will keep on changing, and then you will have the p column. Okay, this is the right tail from the test statistic, which is right here. So if you have degrees of freedom to be 2 for the numerator, as was the case in our example, And then now degrees of freedom for the denominator was 42, but the table, see, they don't have for every value. So that's a bad thing about using tables. You will not get the most accurate answers, but you can use software. Minitab is very handy, or even Excel uses it. If you have any questions, we can talk about it when we do problems. Now, of course, we have to get to the closest one, which is 30. Okay. So if you come up with a statistic of 2.49, the right tail probability will be 0.1 if the numerator degrees of freedom is 2 and denominator degrees of freedom is 30. Okay, so then um, so that's how it is. Now I think the table goes as far as in here, so that's why actually look if you look in here 8.77 goes has a right tail of p equal to 0.001, and then look 14.02 on the x-axis will be much to the right of 8.77, so the p-value which will be much smaller than 0.001. So which says that p is so much smaller than 0.001. Again, the same reason why we reject H null is because p is small. So small p leads us to rejecting H null, which means you are accepting HA. That means there is at least one pair which has its means to be different, right? Okay, so this is like this is just the F statistic, how it varies. Of course, it is also not symmetric. There is a hump usually, but it's not shown that well in here. So you can see 14.08. This is what we got for that example. The p-value will be what is on the right side. It will be much less than 0.001 because p-value for 8.77 is 0.001. Okay, all right then. So okay, so now here's the summary of the ANOVA that we did. So we had our null hypothesis to be that all means are the same. There were 3 of them. HA was that at least one pair of the means differ, right? That means there will be at least one pair whose means will be different from each other. And then the statistic that we got was 14.08 with numerator degrees of freedom to be 2, denominator to be 42, and then p was 0.0021, and then so results were significant to reject H null and accept HA. What HA here says is that there is at least one pair, okay, which has its means to be different, but which one we do not know. Is it that mu1 is different from mu2, or mu1 is different from mu3, or mu2 different from mu3? We do not know. We need to figure it out. Now for that one only we do that multiple comparison, okay. So in fact they have given the results in here. This is like this is the typical way that you will see the results if you were to use SPSS. Okay. In fact, I think I will, for the problem set, I will put some examples similar to this. Now here this is optional. If you want, you can go over this. What this is saying is that if you do ANOVA with only 2 groups, that will reduce to the t-test that we discussed back in chapter 12, I think. Okay, so so actually ANOVA is an extension of the t-test for 2 independent means that we discussed in chapter 12. Okay, all right, so then let's go in here. So now to see which means are different, we need to do step 2, right? So that's what we need to do. They are called multiple comparisons. Now, of course, so multiple comparison procedures, there are several of them. Now see, this is a SPSS screen. All these, there are all kinds of different multiple comparisons. Typically 2 keys, one is quite popular, then Ferroni, and there are like advantages and disadvantages of each one of them. I mean, of course, you can ask for all of them when you do a software, and then it should give you results. Important thing for us is, how do we interpret the results? Of course, that these slides give you the theory behind everything, but you don't have to worry about them. But I'll just show you. This is the LCD procedure. This was the first multiple comparison that we saw in that SPSS screen. So, I mean, lot of common sense goes into this. If you sort of carefully look into this, this is just a comparison between two means. It is just a t statistic. Okay, once you know that there is at least one of them, you sort of look at it pairwise. So that's what you do. This is a very straightforward. But see, now the other multiple comparisons have made certain modifications to this, to make it a little bit more sophisticated, I think. Okay, so once you have, so this is like a typical multiple comparison result. And then see now how you read this. Let's understand this. So you have the pairs. So this is the group 1 to 2 comparison. This is group 1 to 3 comparison, like that. So you have altogether, several different pairs. Then you have 2 to 1 and so forth. Okay, now 2 to 1 and 1 to 2 are the same, right? So now look, out of this you can see that, okay, there is, okay, definitely group 1 and 2 differs. Group 1, remember, is the pet, and group 2 was the friend, right? And then group 1 and 3, that also differs, but not as much as between group 1 and 2, but still it is significantly different. Now, I was curious about group 2 and 3. Remember pet and no, not pet, the friend and neither. They were kind of close to each other. Now, the p-value has decreased, but still there is a statistically significant difference. So, what this is saying is that all three groups are different from each other. Okay, at 0.05 level, or at 0.05 level, 1 to 2 is different. I mean, 1 and 2 are different, 1 and 3 are different, 2 and 3 are also different at 0.05. Okay, so that's how you read the multiple comparison results. And then I think the remainder, like typical, let me just show you. It's just working. If you are curious, you can do this. Now here's Ben Ferroni. It's another multiple comparison. I'm not going to go over this. But see, because using lots of software, you can get the results, but we need to get experiences in reading the outputs. Okay, now assumption that we talked about, for the ANOVA to work well, you need to have independent observations. You need to take if you take the heart rates, the patient observations should be independent from each other, and the means, all these three different group observations should be normal. Okay, and they all should have the same variance. Now these are assumptions. Now there should be ways to check whether assumptions are valid. So equal variance, that means this is called, if you have equal variance, it is called homoscedasticity. If you have unequal variance, it's called heteroscedasticity. Now there are tests to test for homoscedasticity. I mean, I don't want you to know that for the test, but I just want to show you. So assessing equal variance. So this is the most important. And then even like by looking at the standard deviations, you can get an idea. That's what this is saying. Like, if the standard deviations for each different group is very much, different from each other, that means the variances are different. And even like if you look at stem plots, if you have that the box dimension to be very different from each other for the three groups, that means the variability is different. Okay, that means equal variance assumption is not valid. Okay, so this is one test for equal variances. Don't worry about it for this class, but I'm just letting you know. If you do a grad level class, definitely you will do this. And then so that's the output. And then so again, it is just you know, some what can I say, um, some steps to follow here. um, yeah, these again, now see, this is like, these are good things to do if you do analyze data, but I think this will be addressed in a higher level classes, typically in advanced level, like typically in grad level or at least senior level classes. Now if you do not have these assumptions like normality or even equal variance not satisfying, you cannot use ANOVA. Then you have to use something called non-parametric methods. Non-parametric means you don't assume any normality assumption. You don't assume that data will come from normal distributions. Then of course, this is a topic by itself, so I'm not going to go into that. But just to expose you, okay? So that's crystal bodies. That's a non-parametric. Um, and then let's see, so it's just the output, um, and then they have discussed another example. Okay, so when you have the time, just go over it, and then but please remember that you're not responsible for non-parametrics or equal variance assumption tests and stuff like that. Okay, all right, so I'm going to stop here.